Hi everyone. Today we're going to introduce the Infrared Security Alarm Lab. This lab is comprised of several building blocks. Today's first one starts with a pair of LED and a phototransistor. That when we are blocking the phototransistor, the output becomes high, and it's going to be amplified through a comparator, the output of which is shown using an LED light. And also is going to trigger an alarm system with a speaker at the end. So starting with the first building block of a pair of LED and a phototransistor, we're planning to have a few milliamps of current for the LED so that when it lights into the phototransistor, its output becomes low. And in order to do that, we need to find out what the resistor values R1 and R2 to be for that. So here's how we can make plus minus 5 volts for the chips. The right terminal of the left channel and the left terminal of the right channel are connected internally so that they can make the central ground. This makes the right terminal of the right channel to be the plus 5 and negative and left terminal of the left channel to be minus 5 volts. We need to also make sure to let enough current to pass through the circuit with allowing enough current limits. We already have hooked up the circuit as follows, that the yellow input is minus 5 volts, the ground is with the black, and the blue is the positive 5 volts. The breadboard is connected as follows, so that the bottom blue line is ground, same as the central blue line, so they are ground as well. Plus 5 volt is the red ground that is the red line that is shown, and the negative 5 volt is also beside that in the central line. So checking the circuit with the voltmeter, we see the minus 5 volts at the top when we are looking at the negative 5 volts, and we can verify the other channel to be plus 5 volts, as you can see here. This is purely DC measurement, and we can verify it again. So in this section, we are connecting the LED in series with a resistor to control the current flowing through the LED. As you can see here, the LED is connected to a 5 volts power supply. So here we are trying to find out the correct resistor values for the currents. So the first branch is for LED that we choose with a choice of 1K resistor, we can get on about 5 milliamps of current. The second branch is the phototransistor that we can choose a relatively high value of 100K or 200K so that the output can swing somewhere between 3.2 up to 4.9 volts. And in this case, we are hooking them up as follows. The LED and the phototransistor are exactly facing each other, and both of them are in series with their respective resistors, as you can see. And they are both powered by plus 5 volts. And you can see in the voltmeter that when the phototransistor is obstructed, the output voltage becomes about 4.9 volts as opposed to about 3.2 that comes at first. So here, the next part of the experiment is about designing a comparator so that the output of the first stage can be amplified and saturated into a certain voltage. You can see that the comparator's input can be one from the output of the first block, but the other input could be a voltage division. So the comparator is made up of 741 op amp. As you can see, I can find its data sheet at the end of the manual. 741, we need to make sure to take a look at the indicator. So let's dive into the theory of the comparator that we are going to make. The threshold that we are choosing is about 4 volts, somewhere between the minimum and maximum of the output of the last stage. We need to make it through a resistor divider that feeds the negative terminal of the op amp, in this case 741, the layout of which can be found at the end of the manual. In order to get to a threshold voltage of about 4 volts, we are designing our resistor pairs as follows. The bottom one can be 680 ohms, and the top one is about 100 ohms. So in this case, that leads us to the negative terminal to sit at around 4 volts. So here is the circuit that is connecting the comparator, as you can see here with the chip, to the first stage, the output of the first stage. So now we are going to test that how the output is going to change. The input and output of the second stage is going to be taken from the first stage, and also it's powered up with plus minus 5 volts, and also the resistive divider. It tries to get the threshold voltage of 4 volts. So the output now becomes minus 3.76 volts at first when there's no obstruction, but when we obstruct the pathway, it becomes about 4.5 volts as the maximum. So there is a huge swing. So in the next session, we are trying to make the multi-vibrator oscillator. So in this case, the op-amp is being constructed in both positive and negative feedback. The positive feedback is a pair of resistor divider, and the negative feedback is an RC circuit, as you can see here. In the choice of the components, we've chosen the capacitance to be the maximum, so that the noises would be minimal, and the frequency of operation, which is about to be 300 hertz in our choice, takes us to an RC level, which is a rough approximate of time constant to a resistor of about 1K, that we've tried to include a higher value of about 10 or 20K to make a more accurate value. As you can see here, the multi-vibrator is already constructed using the op-amp and also the 4.7K capacitor with the proper feedbacks, as you can see here, are constructed. And the oscilloscope also shows that the output of the multi-vibrator that is about 260 hertz, as we can see here. And that's so in this section, as you can see, the whole circuit is hooked up. The first segment is the comparator. The second one is the multi-vibrator that on its own was able to create the signal. At the end, the output of the previous stage are consecutively connected to the input of the next stage, and also there is another buffer that is showing right now at the output, allowing us to drive the speaker. And now when we are obstructing the input, there is a noise that you can see how it's going to be heard in the output from the speaker. So every time that there is a blockage, there is a noise coming from the speaker. And that's it for this experiment.